We're now going to talk a little bit about sharing and why sharing, when I say that two atoms share electrons to make a bond, sharing doesn't mean equally sharing. When you have two atoms making a bond and both atoms are identical, then yes, there is an equal sharing of electrons. We call that a non-polar bond or apolar bond. So apolar bond is a bond in which the two atoms have equal strength to attract those electrons that are being shared. None of the chlorines is stronger than the other, and then the corresponding bond is apolar. It's the same if you have the molecule of hydrogen, the molecule of nitrogen, the molecule, any binary homonuclear molecule. So it's only made of two atoms, and excuse me, this should be a nitrogen, and it's only made of two atoms, and they are the same type of atom, will have that apolar character. The electron pair, or in the case of the nitrogen, the 3 electron pairs are equally shared between the two atoms. However, in most cases, you will have a bond made of 2 different atoms. So let's say, for example, a bond between an oxygen and a hydrogen. That's okay, like in the molecule of water. So you have H2O. Let's draw the molecule of water here. You've got 2 bonds between, you have 2 bonds of an oxygen with hydrogen. In this case, the 2 atoms are different. Oxygen and hydrogen, they are in different parts of the periodic table. Oxygen is way towards the right, hydrogen is right at the top of group 1 towards the left. They have different characteristics. They have a different strength to attract those electrons that make part of the bond. So in this case, even the oxygen and the hydrogen are sharing those 2 electrons. The electrons will spend more time in the sphere of influence of the oxygen. They will be more attractive to the oxygen nucleus than they are to the hydrogen nucleus. When you have that, you say that you have a separation of charges. So the electrons in that bond, they are not equally distributed. They are more towards the oxygen side, and they spend less time near the hydrogen. So what we do to signify this is writing a minus in the element that has the negative side, the one that attracts more the electrons, and a plus in the atom that does not attract the electrons so much. But not only that, because it's not that the oxygen has the electron and the hydrogen doesn't have them. No, they are being shared. It's just they spend more time in the oxygen. So to show this, instead of just putting a minus and a plus, we put the letter delta. And delta stands for partial charge. So partial charge, we use the letter delta to show it. And then it could be positive and negative. So when you see a delta minus and a delta plus, that means if you have a delta minus, that's a partial negative charge. It means in that bond, the electrons spend more time, yes, being shared between the oxygen and the hydrogen, but they spend more time in the sphere of influence of the oxygen. They are more attracted to the oxygen. And if you see a delta positive, a partial positive charge, that means in that bond, that atom, in this case our hydrogen, is less able of attracting those electrons that form the bond. So here we've got the example of hydrogen chloride or hydrochloric acid when it's dissolving water. You've got a hydrogen making a bond with a chlorine. They share 1 electron pair. However, the chlorine is more able to attract the electrons from the pair. It's stronger in its ability to attract those electrons from the pair, that are making the bond. So although the electrons belong to both the hydrogen and the chlorine, they spend more time under the sphere of influence of the chlorine, and that's why the chlorine gets the partial negative charge, and less time under the sphere of influence of the hydrogen, and that is why the hydrogen gets a partial positive charge. So the plus and the minus tells us which one is controlling the electrons, which one is not controlling the electrons, and the delta says that this is a partial charge. It's not that there is a splitting of the charge and one is positive and the other one negative. Is that in the sharing does not equal sharing, the electrons from the bond spend more time near one of the atoms, in this case our chlorine. And how do we know which one is the winner when attracting an electron from a pair? Well, electronegativity tells us that. Electronegativity is an invented scale. Pauling invented it in the early 20th century. That is a comparison of all the atoms of the periodic table, and it tells us how good they are when they're in a covalent bond, how good they are at attracting electrons from that bond. This might be a good time for you to have a look at the periodic table trends and look at electronegativity and to see where are the atoms with the highest electronegativity and what are the lowest ones. If you remember electronegativity, you will be more capable of, if you look at my terribly drawn periodic table and you look something like this. When you go up a group, electronegativity increases. Electronegativity can be written with this Greek letter. You will see it in some places. Use that Greek letter. So the smaller the atom and the more you go up a group, the smaller they become, the closer to that electron will be to the nucleus. And although you have the problem with the hydrogen is so small that actually that electron is too close to the nucleus and there's a lot of repulsion with the other electrons circulating around. And the more you move towards the right, the more electronegativity increases. If we ignore the noble gases that are famous for not making bonds or making very few, the most electronegative atom of the periodic table is fluorine. In a competition with 4 electrons in a bond, fluorine will always win. It will always attract to the electron from the pair. Oxygen is another good one, except fluorine, I think, is the second with the highest electronegativity. So when you have a bond between a fluorine and another atom, or an oxygen and another atom, fluorine and oxygen will always be the winners. In general, the halogens, so the fluorine, chlorine, bromine, etc., are good in terms of, when they compete with electrons, they are good at attracting the electrons from the bond. When we have many bonds, okay, so that's a single bond between 2 atoms, and you can always see which one is stronger to attract the electrons from the bond. So what if you put them in a molecule? Well, when you have them in a molecule, you have all these covalent bonds, and they might be pulling or not pulling electrons in different ways. Let's have a little example. We've got here the example that I gave before of hydrogen chloride. And I've told you chlorine is much more electronegative than hydrogen. Chlorine will have the partial negative charge and chlorine will have the partial positive charge. I can draw that like this with the deltas. I can draw them with an arrow, and the arrow points towards the one that is attracting the electrons. Or I can draw them, if I'm feeling a bit creative, as something like this, plus or minus, which is trying to show us how the electronic cloud might look like. So what it's trying to show is that you have an electronic cloud around that hydrogen and chlorine combo, and those electrons are not evenly distributed everywhere. They are actually more towards one side. The side of the chlorine is the one that controls more the electrons. So that's how you might want to show a dipole. Here at the bottom I've got the molecule of water, H2O. Oxygen is, after fluorine, the second most electronegative atom of the periodic table from memory. So in a competition for electrons, of who is stronger attracting the electrons, the oxygen will always win. And the 2 hydrogens they still have, those electrons are being shared by all means, but they are not being shared equally. They will spend more time around the oxygen, around the sphere of influence of oxygen. So if I wanted to draw that dipole, I would draw something like this, because that's the shape of the molecule, and then you will have a section of the molecule that is lacking charge it doesn't have a positive charge. I would say more that it's lacking electrons, and an area of the molecule where the electrons are mostly concentrated. So then if I look at the oxygen, and sorry, this is the molecule of CO2 that I've got there. Again, between the oxygen and the carbon, the oxygen is the one that is stronger than carbon to attract the electrons from the bond. It's more towards the right, it's more electronegative. So the oxygen, the two oxygens will get a partial negative charge, and the carbon will get a partial positive charge. So if you look at those two oxygens, one is pulling from the electrons from the bond towards its own side. The other one is also pulling from the electrons from the bond towards the other side. They are equally stronger in pulling on those electrons because they are both oxygen, so they have the same electronegativity, the same ability to attract those electrons from the bond, and they're pulling in different directions. So that means that although individually the two bonds are polar, so you have CO2 is composed of two CO bonds, double bonds, and those bonds individually are polar. However, the combination, because the molecule is linear and the oxygens are pulling in opposite directions and with the same strength, that molecule is apolar. So just because you have polar bonds doesn't mean that the molecule you end up with is polar. It will depend on how those atoms are distributed. If you have atoms that are pulling in different directions and they compensate each other, you might end up with a molecule that is non-polar, as is the case of the CO2.